Hello, this is Jeff Hamrick at Rhodes College, and I'm going to talk about constructing a confidence interval for the interquartile range for a few minutes. While in certain cases there are explicit formulas for constructing this particular type of confidence interval, they're not that easy to use, quite frankly, but the technique that we've been using, sampling with replacement, is remarkably flexible and can be deployed in this situation to quickly estimate what the confidence interval for a true IQR is. So imagine I'm working with our body temperature and heart rate data set here. Imagine that I'm interested in the interquartile range of body temperature, and to access that statistic quickly I can add a 5-number summary to this basic summary table, and we see that the Q1 and Q3 are respectively 97.8 and 98.7. So I could, for example, right click on this and add a formula, S7, and I'm actually going to just add IQR explicitly. And we see that IQR is in fact 0.9. That's of course just a point estimate. That's our best guess as to what the true interquartile range of body temperature data is, but I can use sampling with replacement in fact to get a better sense as to the range of values of the interquartile range that are plausibly supported by our set of data. So what I'm going to do here is right-click on right-click on temperature resting heart rate and sample cases. I want to sample with replacement, so I'm going to leave this option checked off. I'll kill the animation and I'll allow the replacement of existing cases. I want to replicate the behavior of the original group of data. Recall that this set of data has 130 cases in it, so I'll sample with replacement 130 cases at a time. And if I check out this table here, I see that it does indeed have 130 cases in it, but some of them are duplicates of one another because I'm sampling with replacement after all. The measure I'm going to impose on this sample is the interquartile range. So I'm going to call this IQR simulated, or how about IQR resampled? I think that's a slightly better description. And the formula will be IQR of body temperature from the sample, not the original set of data, but from the resample. Okay. In this case it was 0.9 again, but that may not always be the case. Now that I've defined this measure, I'm going to collect measures repeatedly. Okay. 5 is not going to be enough, as you might expect, so I'm going to turn the animation off here, replace existing cases, and I'm going to collect a much larger number of measures after deleting this table. I'm going to collect something like 1,000 measures, and this takes a minute to run in Fathom, so I'm going to go on ahead and pause the screencast while I start having Fathom collect these measures. Okay, so Fathom just finished collecting 1,000 measures, and I want to take a look at those, of course. I'll table off of this collection of measures, and then I'll create a dot plot of the randomization distribution. Okay, we see that because there's only really sort of a finite number of combinations of samples that can be taken with replacement, we get the same values for the interquartile range much of the time, but there is some variation that's justified by the original set of data. So this set of data, this set of randomization randomized measures is not particularly symmetric, really augmenting the need for us to use the switch trick. Let's go on ahead and impose the switch trick on this plot. I'm going to plot a value. Okay. The first value I'm going to plot is the measure taken with respect to the original set of data, in this case 0.9. Okay, that's right here. It's the value we most frequently see when we sample with replacement. That's not surprising. And then I'm going to actually plot a new value that's going to be equal to twice the measure we observed for the original set of data minus the high percentile. So in this case, for a 95% confidence interval, the 97.5th percentile. And I get the value of 0.7 right here. So that's going to be the lower bound of our confidence interval. And now I want to get the upper bound of our confidence interval. That's going to be twice the measure that we saw with respect to the original set of data minus a low percentile of the measures that we randomized and collected. And that gives us this upper bound of 1.1. So I would say that I have 95% confidence that the true interquartile range of human body temperatures is between 0.7 and 1.1. Hopefully this example helps you to see how sampling with replacement is a particularly flexible means of estimating confidence intervals for almost any type of measure.